What I want to do is spend a bit of a time to discuss about the service provider challenges that we are seeing throughout the industry. And the reality is that if service providers are going to survive in the years to come, they need to readapt to the new world. We are now moving towards the cloud. A lot of customers are moving towards the cloud. And so what we are seeing is that there is a push for bandwidth in the service provider space. And the revenue is reducing across the service provider space more and more, right? Flat revenues, declining revenues, a bit of a problem for service providers. So how do they survive in the new world? Well, the move to 5G on one hand is going to drive a bit of a problem. So declining revenues, flat revenues for the upcoming years. But on the other hand, new opportunities for the service providers to monetize additional services. So at the edges of the network, they will be able to provide additional services for their users. So IoT would be one example, augmented reality, virtual reality, all of those would drive new revenues. And at the end of the day, it's all about saving money. It's all about finding new ways to monetize the network, right? Changing the way they are architecting their networks, changing the way they are building their infrastructure. And that's exactly what we are going to spend time on today. Right, so what we've seen across years is that the big cloud providers have actually been extremely successful in re-innovating themselves and being able to drive new architectures into their deployment to support new services for their customers. And what the cloud providers, the Googles of the world, the Microsoft, Azure, every one of those have moved away from rigid architectures into scale-out models, where adding additional capacity in the network introduced the ability of scaling out the network in a more seamless way, introducing capacity for supporting their services. At the end of the day, it's all about simplification of the services. It's all about introducing software control and programmability across those networks to support that end-to-end automation, right? Moving away from proprietary architectures, moving away from those scale-up models of the past into more flexible deployment models. And one of the key aspects comes from the physical infrastructure as well. Instead of relying on vendor-specific proprietary silicon, some of those cloud providers are now relying on merchant silicon. And that merchant silicon drives innovation. An example of this would be the move from 100 gig networks to 400 gig networks, right? The big cloud providers are not having second thoughts at this, right? At any point there is new innovation, they are pulling out the infrastructure, they are deploying new devices to support that end-to-end new capability. And so that's exactly what we think the service providers should do as well. They have to have more flexibility in terms of how they approach their infrastructure. And this is the current state across the service provider space. What they are doing today, they are running multiple parallel networks. And those networks serve different purposes, right? Siloed networks to support wireless services, to support business VPNs, internet services. We all know the drill. At the end of the day, multiple teams operating very separate deployments across the service provider space, kind of like different companies operating inside the service provider, right? But that's not efficient, right? Because you're dealing with multiple proprietary architectures, you have multiple orchestration systems, you have multiple operational tools that you are deploying on top of those networks, right? So that becomes very complex very soon. And so what we've seen with the big cloud guys is that they were able to simplify their deployment. They were able to operate a single network for all of their services. And that's exactly where the service providers would need to go. Operating a single network introduces a big scale-out model, resilient architectures, the ability to implement programmability and automation across the deployment, and having a single stack in terms of the management and automation layer. And obviously, at the end of the day, that saves a lot of money, right? And that's exactly what we are seeing across the cloud provider space, and the fact that the service providers are now looking to reinvent themselves to support this. And if we take one component of this particular puzzle, the infrastructure, there is a key aspect in here. Across time, what we've seen is that things have become more simple. In terms of the protocol stack, service providers are simplifying. No longer they need to deal with frame relay network, ATM networks. Things are becoming a bit more simple. right? So we are now at an inflection point, simplicity, and then the merchant silicon throughout the industry is picking up in terms of capability, right? So we are now at an inflection point where a traditional switch can actually become a router. We can now support on silicon features such as segment routing, MPLS, EVPN, VXLAN, right? So those things are going to help the service providers drive new innovation on top of their network without necessarily having to think about purpose-built devices, very expensive scale-out devices that they need to deploy across their infrastructure. They can now collapse everything into a 1RU device. They can deploy their network using a more efficient architecture. And merchant silicon is going to be the core of this implementation. A perfect example of this is the Broadcom Jericho chipset. This was introduced in 2016 and supports features such as MPLS, VXLAN, EVPN, and that's part of the discussion today, how we will leverage those protocols to be able to deliver a modern service provider architecture. And it's not only us saying this, right? This is an example from Netflix. Dave Temkin is one of the VP of networks at Netflix. What he mentioned is that they removed the last big expensive router from their infrastructure. Commodity switches are running the entire Netflix Open Connect CDN right now. And if you think about Netflix, at the end of the day, they are in a way a service provider. They are serving their users, right? They are bringing traffic all the way to their services, right? So the line is kind of blurring between what service providers are and what cloud providers are. And in terms of building that modern architecture, on one hand, we discussed about the infrastructure, but on the other hand, we need to discuss about what powers that infrastructure. And it's the operating system that you're running on top of those devices. And what we need to do is to look at operating the network using a modern operating system. A lean OS programmable at all layers to achieve that end-to-end automation across the stack. Spine leaf optimized. Instead of big scale-out models, big routers, we are now looking to deploy a scale-out deployment, 128-way. Adding nodes within the infrastructure adds additional capacity. Automation, netconf, YANG models, large scale-out ECMP fabrics change the way we need to monitor the networks as well. If you think about the networks of the past, right, we used to rely on SNMP and logging. Those were the main mechanisms that you would use to actually drive information about how your network is operating. Well, that has to change. In a big scale-out implementation, no longer can you rely on those tools. So right now, we need to flip this. We need to look at telemetry streaming from each and every device in the network and being able to make intelligent decisions in real time on how am I consuming my network, how my network is operating. And so if we look at the traditional service provider architecture, this is the starting point in the conversation. We have the users, the consumers of the service, and it used to be about those building blocks. I'm going to build my infrastructure using an access, aggregation, core layer, peering layer, and eventually I'm going to bring my user to the actual service that they are consuming, be it internet, MPLS services, IPVPN services, a very simplistic approach. But the reality is if we take this approach, then we are only about transport, and we don't have any option in monetizing those additional services across the infrastructure. And so what we are seeing, as we said, is that the service providers would need to reinvent themselves. Right? What we have here is the new world, where we are driving additional capacity or capability across the network. So NFV services, for example, edge compute services to support those new type of applications, IoT, augmented reality, virtual reality. And so everything starts to look more like the cloud. There are a lot of pockets in this infrastructure that look like a leaf-spine cloud network. Right? So this has to be driven in a different way than the traditional models. And so the key aspects that we mentioned is the fact that we need to move out from the scale-up models of the past, big routers, where we used to deploy this using single vendor solutions. And in terms of actually adding additional capacity, it used to be about, I'm going to pull out this box and put in a new one. That's not very efficient at all. It's going to cost a lot of money day one, and it's going to cost a lot of money to replace this with new architecture in the future as well. Forklift upgrades at the end of the day. Upgrades are also very hard in this deployment model. Obviously, when you need to upgrade a box, you lost 50% worth of the capacity across the infrastructure, right? Whereas if we look at the model on the right-hand side, this is what has been very successful in the cloud provider space, that scale-out deployment with 128-way ECMP, where we are driving this in a leaf-spine architecture. What's the advantage of this? Well, you put in a new device, you have additional capacity end-to-end. You need to replace parts of your data center, you're not replacing everything, right? You deploy that new box, you get that 400 gig capability that you have in that new device, right? So it changes the way you're architecting the networks and introducing additional scale in the deployment. Hitless upgrades is one of the key aspects of what the big cloud providers have driven across those architectures and what the service providers would be using in their deployment model as well. And obviously, in terms of the upgrades, the impact is different. No longer you're bringing down one of the box and you're relying on the remaining one. You upgrade one part of the data center, and then the rest of the data center continues to operate. All of those hundreds of boxes are still there to take the traffic, right? And so if we look at the big picture from 10,000-foot view, this is how the service providers would start looking like, more like a cloud provider. A lot of leaf-spine architectures to provide that compute capability that they need for the NFV services, for the additional services that they will be exposing to their users at the edge, and then transport in between those locations, right? And a perfect example of this is AT&T. AT&T AIC, or AT&T Integrated Cloud, is an example of where this has been done before. Across US, AT&T has deployed hundreds of data centers where they have an OpenStack deployment, and they also have containerized applications to serve additional applications to their users, right? So NFV platforms, telco apps virtualized instead of being physical, a lot of those methodologies that change the way service providers operate. So what we will do next is we will look at this particular picture and kind of zoom in into the protocol stack of how this could be built, both from a data center perspective, but also in the wide area network in the core metro deployment. So if we look at the transport layer, how do we move traffic from point A to point B? MPLS has been used for quite a while in the service provider space, and it has been very successful across years. And to be honest, it's quite flexible. So we believe MPLS should still be the core of the deployment for a service provider network. But the reality is that there is a need for more flexibility in how we shift traffic from one location to another. And this has been tried, wasn't really successful with RSVPTE. Segment routing, we think, would be a good candidate for solving this problem. And what we do in this particular case is we use a central intelligence, a controller within the network, to understand the network at a holistic level. How much bandwidth am I deriving on top of each and every link, right? What's the quality of the links? Do I drop any packets, right? And based on this information, I'm able to take more intelligent decisions on how to consume the available resources across the end-to-end service provider deployment. And segment routing would sort out that path selection across the infrastructure. So that could be used in the metro core network. And then how do I drive my services? How do I connect my users to my services? This is on the right-hand side with the BGP VPN services. Layer 2, Layer 3 VPNs that are bringing my users to the actual service that I'm exposing. So in more detail, what is segment routing? A lot of you may not necessarily have dealt with it before, but I think it's worthwhile going into some of the concepts. So segment routing envisions the network as a collection of topological subpaths. They are called segments or segment IDs. And there are different types of segments, either global segments or global labels, local labels. Forget about those for the time being. We will explain what they are. But at the end of the day, what we are doing in the network is we are programming at the ingress of the network a label stack And that label stack dictates the direction of a packet across the network. It pretty much says, I want to get from here, I will hit this particular hop, I will hit this interface, and I will get to my destination service in this particular manner. And who decides what I'm going to do? It's going to be a higher level controller that would implement that logic on top of the end-to-end fabric, right? Now, what's the basic philosophy behind this? Some of you may be aware, if you're coming from an MPLS background, that we used to use separate protocols for label signaling within MPLS networks. Those would be LDP or RSVP-TE. Now, the promise of segment routing is the fact that we are simplifying. No longer do we need to use those separate protocols. We are actually leveraging the IGP and EGP to provide that label distribution across the network. And that removes a lot of the complexity that we used to have with RSVP-TE and LDP. On one hand, with RSVP-TE, some of you may be aware that you need a lot of tunnel state across the infrastructure, point-to-point tunnels. It's pretty complex, pretty clunky. There is no central intelligence on how to actually set up a data path across the network, right? There is no global policy, and that's exactly what segment routing solves. So what's the applicability of this? At the end of the day, traffic engineering, but traffic engineering done in a more intelligent way. So in a bit more detail, segment routing. What segment routing does, it divides the network into segments. They are called segment IDs or SIDs. A label in itself is just a number at the end of the day. And that label gets programmed at the ingress, or a label stack gets programmed at the ingress to dictate what would be the data path across the end-to-end network. As we said, there are different types of labels or SIDs that identify nodes. Those are the global labels or global SIDs. They identify loopback IP addresses on routers. How do I get to a particular router? Or prefix SIDs. How do I get to a subnet, right? And then you have anycast SIDs. Anycast SIDs point towards a collection of routers. Let me give you an example. You want to send traffic to Auckland, and you don't care what specific box in Auckland you are going to hit. You define a series of routers with an anycast SID, and then you point your traffic towards Auckland. Traffic is going to get there. Whatever box is going to be selected doesn't really matter, right? That's what anycast SID would be used for. And then there are locally significant SIDs that identify adjacency links across the network. So once you get to a particular node, you have the flexibility of actually selecting which particular link you're going to use out of that node. So a bit more granularity in terms of the path selection. As we discussed, the SIDs, or the labels, the IDs, the segment IDs are encoded as MPLS labels in the forwarding plane. Now, I know there are a lot of things that are new in here, so let me provide an analogy. So from a segment routing perspective, let's kind of look at what you do day to day, right? You pull up your phone, you use Google Maps, and you want to get to a destination, right? And as you know, within Google Maps, you have a series of constraints that you're able to apply. You would be able to say avoid the highway, avoid tolls, avoid ferries, right? Think of it from the perspective of a segment routing network. That would be your controller. The controller would imply those constraints. I have this bandwidth available. I have packet loss here. I'm going to make a decision on how to consume my network based on those constraints. And I'm going to apply a logic within the network to provide the end-to-end data path, right? And that's exactly what we are doing in this case. At the end of the day, Google Maps is going to give you a series of left and right turns. You can consider them as segments within segment routed networks, right? How do I get to a destination? In terms of a comparison point between the traditional protocols that you would use on top of an MPLS network, you have LDP and RSVP-TE. I'm not necessarily going to insist a lot on this particular table, but suffice to say that we are eliminating the need for that additional protocol stack for label signaling. Segment routing solves that problem together with the IGP extensions or the BGP extensions that are exposed. Natively, equal cost multipath networks are supported within segment routing, something that was very hard to achieve with RSVP-TE in the past. a lot of that per tunnel state that we used to have with RSVPTE networks is gone right now. Everything is programmed into the data plane, the label stack is programmed at the ingress, and you're dealing with that only. So we are eliminating that explosion of state across the infrastructure, and this makes it so much more scalable. Natively, IPv6 is supported through extensions, so it works very well on top of IPv6 networks as well. So what are some of the use cases for segment routing? So at the end of the day, you can do this in the data center, leaf-spine networks, but really it's not that popular in the data center space, specifically because you don't necessarily need to make intelligent decisions on how to consume a leaf-spine network that already has enough capacity. But then you can also consume this in the core. So the ring topology in the service provider space, this is where you're actually driving a lot of benefits out of consuming this end-to-end infrastructure. So solving the ring topology problems allows moving the traffic in an intelligent way across the infrastructure and actually interoperates with RSVPT and LDP through a series of mechanisms that are out of scope for this discussion. So where is segment routing useful? Let's take this example, and I'm going to try to boil it down to very simple terms, right? We have an ingress ASBR. It needs to send traffic to that blue prefix in there. There is not enough control to be able to make intelligent decisions on the exit points across the network. Yes, I can send my traffic all the way to ASBR4, but I would not necessarily have global control in which particular exit point or NNI link I'm going to consume, be it NNI 2.2 or 3.1 on that diagram. Not enough flexibility in the traditional sense. With segment routing, on the other hand, I have the ability of injecting information about the state of the network into a controller through BGP-LS, ISIS over GRE, or a series of protocols. The controller then has this holistic view of the network and would be able to program that ingress label stack to make intelligent decisions on how to consume the data path. A global policy that would allow me to select the exit point and the actual exit link out of that ASBR as well. So much more flexible in terms of the path selection versus the traditional models of the past. Right, so we kind of looked at the transport layer within the end-to-end deployment. Beyond that, we need to look at how to offer services to our users. How do we connect users to other users, or how do we offer service provider-based services, NFV applications, and so on and so forth. And this is where BGP VPN comes in to provide that support. So the advantage of BGP VPN is that it's standard-based. A lot of vendors have support for BGP VPN. Instead of running multiple protocols to actually provide layer 2 or layer 3 VPNs, we can do this with a single protocol. It's very scalable. It's based on BGP networks. It has been proven across the internet. BGP is a very scalable protocol at the end of the day, and allows you to advertise both MAC addresses and IP prefixes, which makes it an ideal candidate, as we said, for both layer 2 and layer 3 VPNs. In terms of the encapsulation types that are supported, we can drive this on top of MPLS networks, or otherwise we can drive this on top of pure IP networks using VXLAN. So very flexible from a transport level perspective. This is not scary at all. If some of you have experience with MPLS networks and they have ever stood up layer 3 RFC 4394 VPN, they would know that they would use route target imports and exports to be able to pull information about a particular VPN and become a participating member within that VPN. Those are exactly the mechanisms that we use for eVPN as well. Route distinguishers, route targets, we are pulling those and pushing those to become a participating member within a given VPN. Those are just some low-level details on how an MPLS Type 5 route looks for a Layer 3 VPN. Not so interesting. What I wanted to highlight in here is the fact that you are reusing the same concepts as today. Nothing changes if you're operating an MPLS network. In terms of the end-to-end deployment, this is how it might look, right? So you have 2 data centers, you have services across those data centers. You're using BGP VPN to establish communication and establish a VPN between different services across those geographical locations. And you can do so at both layer 2 or otherwise layer 3 as well. And finally, in order to become more intelligent in that path selection, in driving those algorithms to provide that path selection across the infrastructure, we need to change the way we monitor our networks. No longer can you rely on SNMP and logging. We now need to shift the gears and move towards injecting telemetry streaming into a centralized location. And that can be done in many ways. OpenConfig is a perfect example. It has the backing of a series of service providers across the world. AT&T, British Telecom, cloud providers, Google, Microsoft, and so on. And what OpenConfig is practically a unified view of the network without vendor-specific attributes, right? So you're able to drive the network both from a configuration and from a telemetry point of view using a standard, right? So that's going to change how we are going to do telemetry in the future. So in summary, we are moving away from inconsistent operational models to programmable networks, more flexibility, moving away from fixed chassis expensive routers into more flexible platforms and scale-out models, moving away from slow convergence and distributing that into a leaf-spine architecture with rapid convergence, and finally simplifying the protocol stack. Segment routing, EVPN to support that end-to-end service deployment. Thank you very much. Any questions? All good? Thank you.
Cool, thank you very much, Claudio. So next up, we have Richard Wade talking about automating segment routing and traffic engineering, or traffic. Also, we've got, I think, all slides sorted for all the morning presentations so far. But if there's any presentators that don't have the details for uploading their slides this afternoon, then please just come find me and I'll give you the details and you can get them uploaded. Cool. You've already tested hooking in?
I have. So hopefully this will be okay.
Don't need a video or anything like that?
I do not.
Cool. You've got internet hooked up? I have. Perfect. Let's get a drink of water in this.
Yeah, just one moment, just get my laptop synced up. Thank you. Okay, hopefully that's stable. All good? Okay, my name's Richard Wade. I've been with Cisco for about 11, 12 years. I actually spent about 8 of those years here in New Zealand working down in Wellington with service providers here, so some of you may have seen me around before. Today I'm going to talk about a few different things. I'm going to talk about automating segment routing, and specifically automating segment routing traffic engineering. So I'm going to build on some of the material that was presented in the first session, which is really useful because I don't have to go through all the basics again. But I'm going to talk about a few different topics. I'm going to go into a bit more detail on segment routing, concentrating at the transport plane, and then I'm going to move on to how we can use path computation elements and start to try and automate that. And I'll give a few practical examples of how that can be done. So first of all, a little bit of a refresher, then I'll go into some of the current developments of segment routing, especially for those who are a little bit more knowledgeable in that area, and then I'll move on to the automation stuff. So just to set the scene for the discussion, looking at service provider networks around the APJ region, around the Asia Pacific region, there's a lot of different complexities when it comes to trying to automate end-to-end services across the technologies and the infrastructure that service providers have. Part of this is due to many of the service providers having been around for over 100 years and they've got a lot of legacy infrastructure, where at the same time they're trying to build new infrastructure and new services. And what tends to happen is what you can see here on the screen. You end up with different operational teams with different operational domains of control, different technologies within those domains, and their own automation tools and automation methods. Now, what this means is that you have a lot of data, and you have a lot of potentially models or scripts or NMS systems, and none of this stuff talks to each other. In addition to that, you've got the people factor, which means that quite often the people may not talk to each other either. So trying to do end-to-end orchestration and automation and scale these services in the infrastructure is really quite difficult, given the amount of legacy that people are carrying. When we look at the underlying protocol stack, as was discussed a little bit earlier on, we have data center domain technologies where we have things like VXLAN, we have L3VPN in the core, we have L2VPN in the metro and access, or even plain Ethernet in the metro and access. So trying to technically integrate these protocols and these services can also be challenging as well, and it pushes a lot of complexity into the software stack. So if we imagine a nirvana, really what we would like to be able to have is end-to-end service orchestration. And what we mean by that is having potentially some sort of model-based architecture where we can describe our services using something like a Yang model to describe, so let's say, an L2 VPN service or a BGP EVPN layer 2 service across our network, and have that parsed and implemented automatically across the domains, whether that's data center domain, core domain, or metro and access domain. And part of this shift, part of this alignment of technologies is what we were talking about in the previous session and what I'll talk about more today. We're trying to reduce the complexity of the protocol stack. We're trying to remove protocols from this stack and make things easier to integrate and align the technologies across those domains. And this isn't just a vendor push, this is something that's been happening in the IETF and other standards bodies for a number of years. It's taken a lot of work, actually. I'm not going to talk about BGP EVPN services, that was done very well in the previous session. We're going to talk in this session about the segment routing part and the IP now automation part. We talk about this protocol efficiency, this perceived efficiency of segment routing. And it's when you see the protocol stack laid out like this that you can start to understand what we're removing when we go to a segment routing architecture. Whereas today you might be implementing your services using BGP or targeted LDP. You might have BGP-LU, RSVP-TE, LDP, etc. in the transport layer. And some of those protocols might mean nothing to some people in the room. But needless to say that if you are in a larger network or a more complex network and you're trying to manage this protocol stack, there's a lot of config that goes onto the boxes, first of all, and that opens up a lot of scope for finger trouble. Because if it isn't automated, there's a lot of stuff that you can mistype. And it only takes a minor misconfiguration to send networks down a really bad route really quickly. So if we can try and reduce that protocol stack and strip out some of that complexity, and this is real complexity, and reduce it down to something like a common BGP communicated EVPN for layer 2 and layer 3 services, and then we're just using an IGP in the control plane layer, and have this thing running over IP, fantastic. Much, much easier, much cleaner, much easier to understand, much easier to operate, and more importantly, much more easy to automate, because we're working with a much reduced protocol set. So like I say, this is where I'm going to focus today. I'm going to focus a little bit on the SDN control. I'm going to focus on the segment routing layer. So fortunately, I don't need to go into this in as much detail as I thought I might do. Today, segment routing can run over MPLS, so IPv4 with MPLS. So we're using the MPLS label switching mechanism to switch the package to the network. Or it can run over IPv6. At this moment in time, the IPv6 standards and the solutions available for IPv6 in terms of implementation are less mature than the MPLS implementations, as you might expect. So if you're going to look at segment routing today, I'd probably go for IPv4 and MPLS because it's a known technology set and it's very mature. On the control plane, the labels, the SIDs, the segment IDs for segment routing, are communicated using extensions to OSPF or ISIS. In terms of choosing between the two, there's not a lot of difference. If you like ISIS, go with ISIS. If you like OSPF, go with OSPF. In terms of the availability of the features and capabilities between the two implementations, at least from our point of view, we're pretty much equal on that part. The part I'm going to talk more about later on is the SDN controller part. So this part over here, where we'll talk about how an SDN controller can be used to interact with the network to discover the topology in those services, and you can use it to do path computation to implement traffic engineered paths across the network. In terms of the paths that can be implemented using segment routing, we can have explicit paths. So you can implement segment routing in the same way that you might do really statically configured RSVP-TE if you want to, if you really want to go down that route. But if that's what you feel comfortable with, that's fine. You can also do dynamic path computation, and this is obviously where the SDN controller stuff comes in, and I'll talk about that a little bit more in a minute. The primary point in terms of the config and the drive for segment routing is to remove that configuration and state from the network. So all of the packet path is in the header, and again, we'll talk about that a little bit more. I'm only going to talk about two types of segments. I'm going to talk about prefix segments. This slide describes what that is. If you want to get from router number 1 to router number 5, and the prefix is beyond router number 5, for example, then you can use a prefix segment ID, and you put that segment ID into the packet of the header, and the network will find its shortest path first destination to that segment ID. The segment IDs are in the IGP along with the prefixes, so it's all one big combined data set from that point of view. So that the network can find a shortest path to that destination. Because we're leveraging the IGP, we can also do equal cost multipath. So if there are multiple paths to that destination, to that segment ID, if you're only giving a segment ID, then the network will find multiple paths to it and will load balance that traffic accordingly. You'll see this a little bit more clearly in a moment. The second type of segment I was going to talk about is adjacency segment, and again, this was talked about earlier on. This is really just how to get from one node to an adjacent node. Now, the reason that these two segments are important and why I'm talking about them right now is that we can combine these segments in what's called a segment list, and we can encode all those segment IDs into that segment list and put those in the header of a packet to describe the path the packet needs to take through a network. So the diagram on the screen at the moment describes an example segment list. If we've implemented a path where the segment ID list is 16,001, 16,002, 124, 147, to get from node 12 to node 7, we can see that we would go to 16,001, which is here, and actually we have multiple paths to get there. We can go via node number 10, or we can go via node number 11, and the network will take care of load balancing that traffic for us. We don't need to do any additional config for that to happen. We can also add weight to that, which I'll talk about in a moment with policy implementation. The next segment on the list is 16,002, which takes us to this node. The next segment on the list is 124, where we go from node 2 to node 4 explicitly as part of an adjacency SID. And the next is 147, going from node 4 to node 7. So what we've done is we've combined prefix segments with adjacency segments to describe sort of a destination which is remote, and we'll leave it to the network to determine how to get there. But then we've been very specific, and we said, actually, I want you to go from this node to this node and from this node to this node using these links. So you can be more prescriptive in areas where you want to. So this example is obviously, quite a contrived example, just to illustrate the point. And it's also an explicit path example. Now, if we want to use dynamic paths, so we don't want to have that state configured in our network what can we do? So we use dynamic paths. If you want to compute a dynamic path, at least from Cisco's point of view, there are two options. You can do distributed path computation, or you can do centralized path computation. And you don't have to do centralized path computation, at least in our solution. The implementation of the path computation function, we build it into iOS XR, for example, and that feature is available in iOS XR software build. So if you have it installed as the head-end router, you can actually turn on that feature in the head-end router and have path computation perform locally. That would be a distributed form of path computation. If you want a centralized path computation architecture, you can have either a virtualized instance or a physical instance which acts as a centralized path computation element. And then you have a PCEP session and BGP-LS sessions with that path computation element. There are some situations where you need to have a centralized path computation element. And that is when you've got multiple IGP domains, multiple BGP domains, if you want different head ends having disjoint paths, so you need to do that type of more complex path computation, then you need to have a centralized PCE. Now, the reason for that from a multi-domain perspective is that if you imagine one head end in one IGP domain will not have visibility of the IGP table in another IGP domain. So it won't have the information available to it to actually do that end-to-end path computation. So what we have is a PCE that peers into multiple IGP domains, using BGP-LS gathers the topology and IGP information, and it then has the ability to perform an end-to-end path computation. Some people are probably really not going to get a lot of that. That's okay. I've got some pictures later on that are hopefully a little bit more apparent. So if we do have a centralized path computation element, this is the type of architecture that we implement. So the path computation element would peer with each of the domains using BGP-LS, link state BGP. That enables the path computation element to receive information of all the nodes, links, SIDs, all the information it needs from the IGP table, distributed into BGP link state and communicated with the PCE. It then has the ability to have a PCEP session with a router in a given domain, and it can perform path computation on behalf of that router when a path is delegated to the PCE controller. It means that you can have a policy or a very light configuration at the edge of your network, and you can just get the PCE to do the hard work of determining what path a TE path should take through one or more domains. And this is where I'm going to focus a little bit more later on. In terms of segment routing and where it's at the moment, I've put this in for reference really. People are going to get the slides. So if you do want to look up some of the drafts, some of the working groups, some of the links, then all this information is in the slide deck. Segment routing has been going for a number of years. It isn't just a single vendor. It's supported by multiple vendors. It's also being widely adopted by network operators around the world. It's seen a lot of growth in the last, I'd say a lot of growth in the past like 3 years with people actually going to live network trial and deployment. A lot of people are still working on it in the lab as well. So I think we're going to see a wave of this coming through networks over the next few years. So I'm going to go on now to talk about some of the more advanced topics in segment routing, which are, I guess, current developments. And this is leading into some of the stuff that's going to be presented over the next couple of days around evolution towards 5G network technologies, such as network slicing. Network slicing is one of those terms that's thrown around, and a lot of people say it, and not a lot of people know what it really means. So at least from a transport perspective, I'm going to talk a little bit about network slicing and how we can try and achieve network slicing at a transport layer. And even if you're not a mobile network operator and you don't really care about network slicing, it's pretty interesting about some of the stuff you can do with your fixed network in order to enable more complex traffic engineering. Like I said, one of the big drives for segment routing is to make it as simple, automatable, if that's a word, and scalable as possible. We want to remove as much static config from the network as possible. the previous presenter did talk about models and telemetry and those types of technologies, and that's absolutely key for this. We need to start adopting things like Yang-based modeling in the infrastructure, in the service layer, so that we can automate the infrastructure. In some ways, it's like a fly-by-wire system for an aircraft. And we've reached at a point where the networks are too complex and need to move so quickly and change too quickly for humans to be able to move their fingers fast enough. We need an automated system which can manage all of these things for us and act on our behalf. So removing the state in the network, getting that out of the network, that static config, putting some of that state into the packet header, but obviously there's only so much room in packet headers, and that's why on the next slide I'm going to start talking about something that's pretty interesting, which is we're moving away from tunnel interfaces. We're moving towards policy-based networking. Some people call it intent-based networking. So you're saying to the network what you want to happen, not necessarily how you want it to happen. So it's descriptive rather than prescriptive from that point of view. And I'll talk about policy on the next slide. I'll then talk about on-demand policy instantiation, which is another way of making this even lighter in terms of configuration, and then automated steering, about how we can get that traffic onto these paths, and how all this comes together at the end. So automatic SRTE path creation. And if anyone wants to have a separate conversation about this outside in a break and me to explain things in more detail, I'm happy to do it, because I understand some of this might be a little bit advanced. There are two components to SRT path creation in an automatic sense. One of them is a segment routing policy, and I'm going to step through some configuration for policy in a moment so you can see how it's broken down. And then a mechanism called on-demand next hop, ODN networking. If you Google search for these terms, you will get stuff from IETF and other places as well. This isn't proprietary naming from that point of view. The first step is to create a policy. So we do configure a policy in the edge of the network. We can distribute those policies using BGP. So once again, removing even more state from the network and getting it up into the controllers and the orchestration layer. But if we do have a policy configured on the head end, if we have an endpoint, which is a target, it could be a layer 3 VPN target, for example, we can get that prefix and we can add a color to that prefix. And we can communicate that information using BGP. In this instance, we're using a route reflector to communicate it. But when the head end, which is router number 6 on this diagram, receives that route, it sees it appear, and it knows that it can create and it needs to determine or calculate a policy outcome for that prefix and that color combination. And that's something I'm going to say quite a lot over the next few slides, is prefix and color combination. If those two things stick in your head, you're good, because by the end of this section, it's important. Once the head end sees that prefix and color combination, it can then instantiate the policy and do the path computation and determine a path through the network. So it'll go to its PCE, get a path, and actually encode that path in the packet headers, and there you go, you've got your path through the network. So for a given next hop with a given color, we can implement a policy. So let me show you what this means. Okay, that looks okay. So this is your segment routing traffic engineering configuration. And it's after 10 o'clock, so everyone's had a coffee, so we're all okay. Segment routing traffic engineering. Okay, so this is the policy bit. So this block of config here is the policy bit. We give the policy a name, in this case, the wonderful name of policy 1. This is the color and endpoint configuration part. So we say what color we want to see and what the endpoint is, so what the prefix is. Those two things go together because those two things together instantiate the policy, which kicks the whole thing off. We then have a different type of SID called a binding SID. Again, I'm happy to talk about binding SIDs and their uses offline, but in essence, a binding SID is like a proxy for other stuff. So when a packet comes in with a given binding SID label, in this case 1000, the router will say, I know that binding SID, I'm going to go and do all this stuff and replace that binding SID with all this new label list. So it's basically a macro in a way. I see this binding SID, I'm going to pop it off and I'm going to do a load of other stuff instead. Within this policy, we've got two candidate paths. We've got candidate path 1 and candidate path 2, and we'll talk about what those are in a moment. And as you can see from those, they're somewhat different. Candidate path number 1, we've got a low preference, got preference of 100. This one is a dynamic path, which means we haven't got an explicit SID list, we're not prescribing the path it needs to take through the network. When we describe a policy, we say, okay, I want to compute a dynamic path. What's that based on? What am I basing that path computation on? And it doesn't matter whether you're using a PC or whether you're using the local head end to do that path computation. In this case, we're using TE metric, not just the IGP metric, you're using the TE metric. There are other metrics that we can use, and again, I can talk about that offline. I've not got the time in this presentation to do that. But you've got a few different metrics that you can choose from to do that path computation. In this case, we're using TE. And we can apply constraints. So we can say, actually, I don't want this dynamic path to cross any link which is, or any interface which is colored red, because that's my super premium path, and I don't want those interrupted. So those are the constraints, the metrics, and the preference for that dynamic path. That's candidate path number 1. The higher preference is preference 200, is actually an explicit path. So what we said is that for candidate path number 2, we want to use the segment list that's listed down below. So we've got a SID list here. So preference 200, explicit segment list, SID list 1, here's the SID list, and here are the labels, the SIDs in that SID list. So we've got two paths, one that goes up, one that goes down. So these are the important bits of information. We've got the binding SID that we defined, which is label SID ID 1000. And then we've got a high preference path option, which is preference 200, which refers to the explicit SID list. So that's the path that's going to be selected when something comes in with binding SID 1000. So in the fib, at this head end node, when an incoming packet arrives and it's got SID ID 1000 on the outer label, we're going to pop that, and we're going to replace that. We're going to push on 16,002, 30203, and 16,004, and the packet goes on its way. That's how a policy works. Hopefully that was, if anyone's got questions on that, we can either do it at the end or later on if we've got time. So given a prefix and a color and a policy, when a head end sees that prefix and color, it'll instantiate a policy, create a dynamic path. How do we get the data? How do we get the packets into that path? How do we get them into that TE path that you've just calculated? Well, by default, again, at least this is on Cisco gear, by default, it's basically an auto route announce. It's automatically announced into the table, into the fib, which means that the incoming packets will be automatically forwarded into that new TE path. You can disable that if you don't want that automatically done. What this means is that you don't have any policy routing at the head end. It's very config light. It's pretty much automatic. So if you imagine the mechanism here, we've got some policy on a router, we've received a prefix, we've automatically calculated the TE path, and we're automatically going to route traffic into that new TE path. This is automagic. There's no human intervention here, and nothing's happening from an operator point of view. Just to be clear, so we can route traffic into that TE path as well, not only on the binding SID, so binding SID 1000, but also if we receive packets that are destined for that prefix and color combination as well. This is where things start getting a bit hairy. So, Flex-Algo. So Flex-Algo is pretty new from a segment routing point of view. It is in the IETF, you can read up on it, and there are some things on segmentrouting.net and also YouTube which do describe this, probably in more detail and better clarity than I'll do today in order to give it justice. So Flex-Algo really allows you to slice and dice your network infrastructure in any way that you see fit. Using this concept of coloring links, prefixes with coloring, different path computation algorithms, what we can do is we can define destination prefixes and colors. We can also essentially color the nodes in our network. In this example, on the next slide, I've got a more clear example. But we can do things like slice it into a link cost path, or we could have a delay cost path. And we could do path computation based on different destinations and different colors according to the algorithms that we've defined. So we can use IGP, delay, we can do link affinity, shared risk link groups. So we can slice and dice the network infrastructure in many, many different ways. I'll go on to the next slide because I think that's going to be a little bit more clear. What it allows us to do is easily define multi-plane topologies, and this is when we start hitting the buzzwords like network slicing. So from a network operator's point of view who's interested in network slicing, this sort of thing from an SDN point of view and also from a path computation point of view is really, really important. So what we've done here is we've got a common algorithm, which is algorithm 0, and that's the baseline. So you might just do path computation based on IGP. We've defined one Flex-Algo group, as it were, which is the green group, which is Flex-Algo 128. And the target for that is minimizing IGP metric. We've then defined a red group, which is Flex-Algo 129. And we said for those nodes, you support calculating paths based on delay, not IGP metric. Nodes 0 and 9 are actually members of all these groups. And this is what I'm saying, that when a packet arrives in, based on the destination and the color, you can determine what algorithm you want to use. So what slice that path needs to take. Yeah, some nodding heads. Okay, we're good. So, okay, just to reiterate, packet comes in. If it's got a destination, which is like green color at node 9, it'll use the IGP path computation, IGP metric path computation. If a packet comes in which is destined for node 9 but colored red, you'd use the delay metric path computation. So that would mean that stuff on the red path, on the red plane, needs low latency. It wants to be low delay, and you want to optimize for that. Whereas stuff on the green plane is IGP metric, and all we want to do is minimize IGP metric, shortest path first. We know all that stuff. But that's like a lower cost in terms of dollars path, as it were. So hopefully that's relatively clear. I think I've reiterated. I don't want to keep reiterating the same points on that. But when people talk about network slicing from a transport and SDN point of view, this is the sort of stuff that we're working on. And this is the sort of stuff that segment routing, the direction for segment routing in this way. And hopefully, having talked about policy, on-demand networking, the coloring and all that stuff, you can see how this is quite easily automated and how we can try and remove that config from the network, but it does require support from stuff like path computation. So the second section of what I was going to talk about is on automation for segment routing traffic engineering. So I'm going to talk a little bit about the architecture of how this stuff fits together, and also hopefully do a bit of a demo and how we can pull this information out of the infrastructure and show you how it works. So I just wanted to reiterate this slide. This architecture is pretty important. Most of the SDN controllers, the path computation elements, it's this type of architecture that is being deployed. And so if you're looking for solutions from a path computation perspective, you really need to be looking at how interoperable, what sort of standards are supported from a sort of BGP-LS perspective, from a PSET perspective. You can get path computation elements that can talk to multiple different vendors' infrastructure, provided they're pretty compliant with these types of standards. Because this seems to be a template that we're seeing around many different networks and many different network operators. And whether it's a switching vendor, routing vendor, etc., this is the type of solution that we're looking at. So I'm going to talk a little bit more about that PCE component. So this layered diagram is, it's pretty generic, right? what I wanted to get across here is breaking down the difference between bandwidth-based path computation, so traffic demand-based path computation, and topology path computation. So where you might have a service orchestrator or whatever you're using, I mean, some people call Ansible a service orchestrator, some people want like a Yang-based service orchestrator, some people want quite an NMS-oriented service orchestrator, whatever your flavor of service orchestrator is going to sit across that with your VPN services, your customer services, etc., and it's going to want to interact with these lower layers. Now, in the path computation area, there are two main problems. One of them is in the red box, which is where the rubber hits the road, as it were, where you need to understand your physical topology, logical topology. You want to understand logical inventory to a certain extent in terms of VPNs and services you've configured. You also want to be able to understand near real-time changes in that topology, so that if you do have a notification via BGP-LS that a link has gone down, for example, that you can act on that in a timely manner. That's also where you need that support between things like BGP-LS and PSEP and et cetera, et cetera. Now, where that's different to bandwidth path computation is if you want to ask a PCE the question, well, I want to get from node 1 to node 10, and I need 5 gigabits per second, and I want that pretty much guaranteed. That's a hard question, actually, because that element needs to understand near real-time bandwidth usage on your network, and it also needs to understand the physical and logical topologies and all that stuff going on. So the architecture that I've got here is an architecture, obviously, that I know reasonably well from my work at Cisco, where we have a topology-based controller, which does the job of gathering all of that physical and logical topology and all the BGP-LS, link state, segment ID, all that stuff information. It then passes that or makes that available via APIs to the bandwidth controller. The bandwidth controller only really knows about traffic demands. So it can form a really, actually it's pretty hard maths, doing a bandwidth model for any-to-any point on the network is hard, but it relies on the topology controller to get that topology information. And that can be gathered by SNMP or NetFlow or streaming telemetry or one of these other mechanisms. Right? Well, I'm not going to talk about that today. So I'll talk about what's in the red box. So what's in the red box? Inside the path computation element, the topology path computation element, as I said, it collects using BGP-LS. It forms a multi-domain topology model, and I'll show you what that model looks like in a minute with any luck. It then has a path computation engine, and the algorithms in that path computation engine are pretty much the same as the algorithms that you have implemented within your normal router, at least from an iOS XR perspective. So your iOS XR router can do the same path computations as this path computation element. Hence the distributed and centralized model. You don't have to have a centralized PC if you don't want it. On the PC, it does present northbound APIs, and the reason for that is that this topology database needs to be made available northbound for consumers of that. So it could be a service orchestrator, it could be a bandwidth path computation element that needs that information, or it could be your own operational tools and your own applications, because as I'll show you in a minute, we can get some pretty interesting information out of a PCE using netconf and Yang or even SSH if you want to go down that route. So do I have a time check? How long have I got left?
We've got 20 minutes left.
Oh, 20 minutes?
Yeah,
Oh, I'll have a coffee, okay. Thank you. Never had that before. Normally telling me to get off. Okay, so I've got a little bit of a demo. It's not super fancy. It's a simple 3-router demo of 3 iOS XR routers running a single OSPF area and a single PCE controller. The OSPF is being redistributed into BGP-LS, and there's a BGP-LS session between one of those routers and the PC controller. So I'm not going to muck around in the routers, and the good thing about SDN is you don't care what they're doing so much. I'll look at the path computation element, the PC controller a little bit, and we'll poke and prod that and see what we can get it to do. figured out I can't see my screen very well, but that's okay, we'll work it out. Okay, for those who aren't aware, this is called a Jupyter Notebook. It's essentially a web UI, which allows you to execute code, in this case Python code, on a live system, and you can sort of see the results in real time as you execute that code. It's quite nice for stepping through annotated code where you want to show the results in real time and not have to flick back to like a CLI and do stuff like that. They use it a lot in the machine learning analytics sort of area. Okay, so what we're going to do is I'm going to open a netconf session with the path computation element, and we're going to pull information out of the path computation element using some netconf procedure calls, remote procedure calls. For those who aren't aware of what netconf is, you've basically got two things. You've got netconf, which is a management protocol, an IETF management protocol. It's actually not that complicated. It just allows you to execute remote procedure calls, get config, set config, that sort of thing. You can interact with something called Yang models really well. If you don't know what Yang is an IETF modeling language, and that allows us to describe what a router can do or data that's on that router. So netconf and Yang go really well together. And if someone wants to talk about that in a break, happy to talk about netconf and Yang. So this is, I'll push this onto a GitHub, and I'll send a link. I'll drop the link into Slack a bit later on. Okay, I'm just going to log into the box. Okay, so for those who might be wondering, yes, the password is Vagrant and the user is Vagrant because I'm using a tool called Vagrant to run the VMs, which is the iOS XRV instances that I've got running there. So all that's done is it's opened a netconf session with the path computation element. It's netconf runs on TCP port 830, and it's just logged in username password. So the first thing to do, just to check that this thing's up and running, I'm going to grab the running config from the box, and we'll print it out and just check that works. Yeah. Okay. Let me just see if I can get my laptop over here. Yeah, that's a bit better. Okay. Okay. So you'll see we've got back a wonderful big blob of XML. You either love XML or hate XML, depending on your bent. Now, this is pretty interesting. So yes, you could write a Paramiko script that would log in using SSH and dump the running config and log out again, but it would be unstructured. It would just be a text dump of the config, and depending on which way the wind's blowing, you may or may not receive all of that config, for example. SSH is fine for a little bit of screen scraping, but if you want something that's really deterministic, you know it's going to work, you know it has worked, and it's formatted so that you can parse it and do good stuff with it. Netconf and XML is much more reliable from that point of view. So what we can see is we've got the running config. I'm not going to read through the running config. So yeah, blah, 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 running config. But it's all nicely formatted in XML, which means that you can throw it through your favorite parsing libraries and drag out what you want to. So if you want to, an automatic script that would go around all of your boxes, log in using netconf, pull the config, close the session, and then archive it into a database or stick it on disk somewhere, you can write it in about 10 lines of Python. It's a no-brainer, honestly. So the next thing is, I mentioned Yang, and I threw this in just because we can. When you're working with Yang, the good thing about Yang is that it's plug and play. And we've heard that before somewhere, right? Yang models, when you have a Yang model for a device or a capability or a data structure, the vendors ship their boxes and their operating systems with the Yang models built in to the operating system, because this is how it works, right? So that means that in order to discover the capabilities of a box, i.e. what it can do from a configuration perspective, netconf uses the Yang models inbuilt in the box. It can pull them out and say, oh yeah, I know now what this box can or cannot do, which is really useful from a network management perspective. So from that point of view, netconf and Yang are designed to make this plug-and-play architecture, a reality. And yeah, it works really well. So what I'm going to do here is I'm going to pull the PCE Yang model. I'm just going to write it to disk, I think. Yeah. And now I'll just print it out because I know you all really want to see what a Yang model looks like. So this is what a Yang model looks like. It's really just a little bit like a JSON document, for want of a better phrase. So you can see that really Yang, in terms of what we call a model, is really just a descriptive text document. So this is describing a link. You can see that it's defining a type. It's an enumeration, which means a list of links. We've got a link with a description. It's human readable stuff. This isn't all super encoded, impenetrable stuff. So Yang models are useful, and I'll mention that again a little bit later on, because if you are working with netconf and you want to find a specific piece of data on a box, you need to look at the Yang model to find out what the actual leaf node is that you want to pull out. So you formulate your netconf filter, which I'm going to do in a moment, according to what the Yang model is. So this is what I've just done here. So I've defined a variable called filter, and I give it the string, which is basically a path to the Yang model, and I'm going to get this filter, filtering out all of the data that's on the box, filter it down to specifically what's in that Yang model path that I want, and I'm going to pull that off the box. There is a point to all this, by the way. I'm not just randomly doing stuff. Okay, so what this has done is pulled off the operational information for the topology on the box. So it's come back in XML, but we can see that we've got a topology summary, which is 3 nodes, which we know there are 3 nodes, and we've got 3 prefix SIDs, and we've got 6 links, blah, blah, blah. So you start to see, well, actually, I've made a couple of queries to this box, and now I know how many nodes I've got, how many links I've got. So let's, we can see what's in here. There's all the information about OSPF and BGP and router IDs, and it's all in there. Okay, so I won't label this anymore. Now, if you don't like XML, and you don't like netconf, and you don't like SSH, we can get similar stuff via REST. So if you've got guys that are more web-oriented rather than XML and SSH-oriented, it's got a REST API as well. So if we just format a simple REST API call, and we'll throw that onto the box, and we'll pull the topology information out using REST as well. So all we're doing, REST call, topology, give it to me in plain text, and we need the password. Yeah. So what we get back is a JSON document that describes the topology of that network. So the 3-node network, the data we've got back here in JSON describes the nodes, the links, the IP addresses, all the stuff. It's all in there. So you can see you're not going to want to sit there and read it, but if you, as a network operator, want to get information on what's going on in your network, what interfaces are configured, what is up, what's your OSPF doing, what's your BGP doing, you want to check, for example, that your interfaces are numbered according to your policy of how they should be numbered, you can scrape all that out of this document a lot easier than you can with SSH scripts. Much more reliable, much more efficient. Okay, so this is the final bit. Like I said, I'm not going to go on forever with it. a little quick example of how we can work with this data. So we've got this blob of XML. So what I'm going to do is I'm going to convert that XML into a Python dictionary. And for anyone who's done Python coding, you know that dictionaries are super easy to work with. It's basically a hash table, very easy to look data up, very easy to work with. So we can use XML to dict, which is a known library in a known module for Python. We can import that. We can parse the data, and then we can filter down onto just the information we want. So we filtered it down to just the topology nodes. We can dump out what's in that dictionary. We know the keys are just to the topology node list. And we can print out that dictionary. I'm not going to look at that. We can find out what keys are in that dictionary. And now we can filter it down to just what are the nodes? What nodes are in that in that data I just grabbed? And I can find out that I've got node 1, node 2, node 3. And all that's doing is a simple for loop over the topology nodes in the dictionary, and I'm printing that out. So this is a two-liner to get a list of all the nodes that are in my link state database. So you've got a path computation element that's learned about your topology and your interfaces via BGPLS, and we're making what's essentially a two-line bit of Python code to get a list of all the nodes that are in our network. It's pretty interesting. Well, it is to me now. Now, what else can we do with that? Okay, hang on. All right, no. Right, so this is where I wanted to end up. So this last for loop, it goes over the nodes in the dictionary. It finds all the links that are associated with those nodes, and it prints those out. So what we're doing here is we've got node 1, it's got 2 links. Node 2, it's got 2 links. Node 3, it's got 2 links. So we can find out the IP addresses for those links, what IP addresses at each end of those links. So if you're a network operator who's running some sort of topology with endpoints, and you want to check the IP addressing, or you want to check that your links are numbered properly, this is, with a path computation element, with a controller, it becomes very, very easy to do this sort of thing. And it's very, very efficient in terms of network. You're not going around every router. This is just calls to one router in the system. Okay, the last quick thing I just wanted to show is an example of, so this is a tool that my team built. And it's actually a segment routing demo. So if anyone wants to run through this demo, I'll happily do it in a coffee break or something. We have a list of what we call, I guess, use cases on the left-hand side here. This is a combination of Ansible playbooks along with path computation element and Python. So the UI is, obviously we use a topology library to render the topology. The topology is learned directly from the path computation element. We pull that out, we pull that out using the mechanisms I've just showed you. And then we can render the topology, and we can render the IGP domains, the IGP areas. And we have the path computation element with a session to the network, discovering that topology. So as an operational team, if you want to build this sort of tool, or you want to integrate with a topology system that you have in your NOC, it's actually quite easy using the programmable APIs that we have in the infrastructure to do this sort of thing. So this one just here, the example we've got here is we've got, we can select and deselect different TE paths from the segment routing point of view that the PCE has delegated to it and computed for the network. And we can run through different use cases. So if anyone wants to run through this with me later on, happy to do that and show you how it all works. Or if anyone wants to develop their own, I'll happily tell you how you can do that as well. Okay, I think I'm pretty much done. So. Yep, I think that's everything. Thank you very much. Thanks a lot. Questions is fine, if there are any questions. Hey.
Should work now. All right. My name is Igor. I work for 2 Degrees here in New Zealand. And the question is actually, you mentioned about all of that stuff, which is very interesting. But I think one of the key details is how you actually bind a service, say a EVPN or L3 VPN to a particular network slice, or a particular, if we talk about trying to relate it to the RSVP to a particular LSP, basically, right? So, and I think this is one of the things which you're currently missing. So, and there is no, not easy way to actually do it, and it's somewhat cumbersome actually to do it, and basically on all vendors, including Cisco, I guess, and Juniper and Nokia or Alcatel-Lucent or whatever it's called now. So it's So what's your, as a kind of representative of Cisco here, are you doing any development in that regard, like any new APIs or ways to actually easily do it on the fly, real time kind of thing, or?
Do you mean binding from the endpoint inside the data center and aligning that slice or that SRT path across the network?
More about, like, you have a service, for example, you provide an L3 VPN, and you want those packets from point A to point B use a specific path in the network. So, and you have, thousands of those services particularly, right? And you want every of those services use different paths, right? And this is the interesting point, how
really, I mean, we can talk in more detail in the break, but really that sort of thing should be taken care of by the on-demand network, on-demand next hop, and the SR policy stuff. So if we have an L3 VPN, a BGP communicated endpoint which matches the color of the destination for a policy, then it should implement that policy for that destination. So that should tie, for example, an L3 VPN, EVPN endpoint with a policy that's been implemented in the network.
Oh, yeah. So it's actually, in case of iOS XR, it's done by via the policy, right?
Yeah.
Because it was somewhat complicated in a sense with the RSVPT, where you have to use communities and you bind those particular LSP.
No,
like
it should happen automatically as
All
part
right.
of that architecture I described. Yeah, that's
Sounds
the
good.
plan anyway. Yeah.
I think that's it.
Okay, great.
Oh, right at back. Where was the hand?
It's ambitious. Trying to get hi, I'm Mark from Phoenix. Just a question on OpenConfig. You mentioned about Yang modeling, and OpenConfig is obviously going to be a real boon for the development side. Just having a simplified kind of, I guess, interface to everything. So just a question, I guess, about sort of Cisco's support of OpenConfig and where that's up to and going.
So in terms of the Yang model creation, there are 3 sets really that we implement. There's the IETF standard set, which we're actively participating in helping develop. There's the OpenConfig set, which we also adopt. And then there's the Cisco-specific extensions to those models. So that probably sounds like embrace and extend. It is not. All it means is that where you've got, let's say, an interface spec from something like OpenConfig, where Cisco has additional parameters for an interface, we just basically extend that Yang model with those parameters that are additional to the basic ones. So it's not a case of replacing or rewriting that OpenConfig model, it's extending that model. So you can still use the baseline OpenConfig model in addition to the Cisco-specific one. Yeah. But yeah, absolutely, OpenConfig is part of our model strategy as well.
Cool, thanks.
Okay. Cool, thank you.
So thank you very much for Richard. So we're now at our first break, morning tea. So for that, you head through the doors on your right, and you'll get through to kind of a sponsor and food area. So if possible, please visit our sponsors. They actually pay about 2/3 the cost of NZNOG, so you can kind of do the maths on what your ticket would cost without them. And they give you kind of all the cool swag in your bags. And talking of swag, there's actually some, if anyone's into it, there's some Ansible t-shirts on the front desk that you can kind of pick up as well if you want one of those. Cool, thank you.
Now, don't suspend your laptop, or else it's a pain to get. Well, it's not a pain. You just got to go authenticate to the web gateway.
Yeah.
I spent a long time yesterday thinking, why doesn't my internet work? And it was that. So
So these guys.